All right, picture this. You're driving, tunes are on, everything is totally normal. And then bam, the car in front of you just slams on its brakes. You react, of course, but your car, it doesn't stop on a dime. It keeps going. So the real question is, for how long? How many meters are standing between a close call and a serious collision? Okay, let's break down the physics you are literally betting your life on every single day.
So let's make this real. You're doing 60 kilometers per hour, a pretty normal speed in the city. Something unexpected happens. You hit the brakes hard. How much road does your car chew up before it comes to a complete halt? Are we talking 10 meters? 20? Maybe 50? The answer is probably not what you think. And honestly, understanding it is absolutely critical.
So, first things first, we have to tackle this huge misconception our brains have about speed. You know, we like to think in nice, simple, straight lines. But the real world, especially when you're talking about physics, well, it doesn't always play by those rules. Our gut feeling, our intuition, tells us that if we double our speed, say we go from 30 to 60 kilometers per hour, we're going to need about double the distance to stop. It just seems logical, right? Double the speed, double the braking distance. But what do the actual laws of physics say about that? Yeah, it's not double. It is 4 times the distance. And that's because the kinetic energy your brakes have to fight against is proportional to the square of your speed. So let that sink in. When you double your speed, you are giving your brakes 4 times the amount of work to do. And in the real world, that's the difference between stopping safely and, well, not stopping safely. And this graph right here really visualizes that terrifying math. Just look at that curve. It is not a straight line. As your speed goes up, the braking distance just skyrockets. This is exactly why a small increase in speed on the highway has such a massive and dangerous impact on the room you need to stop. But wait, the car's braking distance, that's only part of the story. There's another huge factor in this equation, and that factor is you. Before your car's amazing brakes can even do their job, your brain has to get in the game. This brings us to the real metric we care about, total stopping distance. This isn't just about what happens when your foot is on the brake pedal. No, it's the entire sequence, from that oh no moment your eyes see the problem to the moment your speedometer finally hits 0. And we can really break this total stopping distance into 2 critical parts. First, you have the reaction distance. That's all the ground you cover while you're just, thinking and reacting. And only after that does the second part, the actual braking distance, even begin. And this whole thinking phase is actually more complex than it sounds. It's not just one thing. It's the time for your brain to process the danger, the time for your foot to physically move from the gas to the brake, and there's even a tiny delay for the brake system itself to build up pressure and fully engage. So you add all those little delays up, and for an average alert driver, you get about 1 full second. 1 second doesn't sound like a lot, does it? But in a moving car, believe me, it is an eternity. An eternity measured in meters. And this is where it gets really eye-opening. At 60 kilometers per hour, in that single second of reaction time, your car travels nearly 17 meters. That's about the length of a semi-trailer truck. And just to be clear, this is all before you've even started to slow down. Okay, so now let's throw the real world into our neat little equation. Because so far, we've been assuming perfect conditions. But as every driver knows, the road itself can change the rules of the game in a split second. Just look at this graph. The difference is absolutely staggering. The bottom line there, that's your braking distance on dry asphalt. The top line, that's what happens on ice. It's all about the friction coefficient, which is just a fancy way of saying the grip between your tires and the road. And on ice, that grip all but disappears. But modern technology can help fight back. This chart shows the magic of an anti-lock braking system, or ABS, on a wet road. By pulsing the brakes way faster than any human possibly could, ABS stops the wheels from locking up and skidding. This helps the tires maintain whatever grip is possible, and as you can see, it can shave off up to 15% of your braking distance. And very often, those are the exact few meters that make all the difference. So what's the big takeaway here? What does this all mean for you, the person behind the wheel? Well, it means that while you can't change the laws of physics, you actually have way more control over these crucial meters than you think. Let's put it all together in one big formula. Your total stopping distance is your reaction distance, which grows in a straight line with your speed, plus the actual braking distance, which grows with the square of your speed. And then that whole sum is multiplied by the reality of the road conditions. So here's the bottom line. Driving is an active negotiation with physics.
Every single decision you make, your speed, your following distance, how focused you are, is constantly changing the variables in this life or death equation. You're not just managing a car, you are managing a buffer of time and space. So the next time you're on the road, I want you to think about that space in front of you. It's not empty. It is filled with your reaction time, with kinetic energy, and with friction. And knowing what you know now, will you ever see that space the same way again?